So we'll see. So this is the planet we need to pick up with. This is our first gas giant. So actually chapter, let's see, is this 6? Chapter 8 talks all about the gas giants. But this is Jupiter. And what famous person actually saw moons orbiting Jupiter? Starts with letter G. Galileo, yep. So Galileo saw Io, Europa, Ganymede, and Callisto. Those are the 4 that he saw. So those are collectively called the Galilean moons. And so Io, actually, this is artist rendition. Okay, so this is not a photo. But basically, Io is this popped sort of thing. And honestly, if we're going to visit gas giants like Jupiter, Saturn, Uranus, and Neptune, our best bet is to really take a close look at their moons, because we can stand on the moon, we can't stand on those gas giant planets. Okay, so this is from Io. Gas giant, we're going to talk more about this in chapter 8, but what does H stand for? What element? Hydrogen, yep. What does He stand for? What element? Helium, yeah. So the gas giants are mostly composed of that. So Jupiter is the biggest. Sometimes he's called a bully in a good sense. He's the biggest in our solar system, and he's kind of actually, if this is the sun, someone stole the sun. Oh, you know probably why, because that chair looked like it was going to fall apart. That stool did. So someone finally took the stool. But anyway, if the sun is there, here's the Earth, and of course Jupiter's out here somewhere. Jupiter actually has been influential in kind of, well, a few things, but kind of like blocking stuff that might have otherwise hit the Earth and inner planets in the inner solar system. Now, the Earth's had its fair share of knocks, but Jupiter's kind of minimized that a little bit. So some people ask, well, Jupiter, you know, we're going to talk about our sun, and we're like, well, if Jupiter was a little bit bigger, well, I think 7 times bigger maybe, Jupiter actually could have become a second star. Because it's all about, is something going to be a star, something going to be a planet? It's all about mass. Okay, so, and actually, most stars out there have companion stars. It is so cool, it's almost like romantic. Okay, and Jupiter begins the gas giants, so what's after Jupiter? Saturn. What's after Saturn? Uranus. Very good. What's after Uranus? Neptune. What's after Neptune? Pluto. I have a slide on him coming up. But anyway, so these gas giants, they all have rings. They all have rings. Now, do we see the rings around Jupiter through a telescope? No. What planet do we see the rings around? Saturn, yeah. But it's got rings, and it's got lots of moons. All right. Saturn, speaking of. If you follow the Twitter feed for this class, on my way to work, I fell upon a Star Talk episode podcast that was talking about exploring the universe. And I got to the part, I haven't listened to the whole thing, but I posted on our Twitter feed. It took 7 years to basically send a satellite or gizmo to Saturn. 7 years, I know. Can you imagine? And even Mars or whatever, you know, a little bit closer to home than Saturn. I mean, the odds of something going wrong, yeah, it's there, you know. So Mars has a lot of failures. Saturn has its fair share of failures. Up there in the corner, does that look like actually, that's a moon. Okay, and we call these moons, how would I say this? I'll do it this way. I would call this a moon in orbit around Saturn. If it's our moon, I use a capital M. Okay, that's our moon. Okay, lowercase m is a something, okay, orbiting another planet. Sometimes they're called satellites. Does that confuse your way? I usually think satellites are man-made, but sometimes they call moons that orbit other planets satellites. And I can never spell that word, but something like that. It's a satellite. Okay? Anyway, does it look kind of fuzzy around it? It's got an atmosphere, and that's kind of unique to moons. Our moon doesn't have an atmosphere. It kind of has an exosphere. Kind of oozes gases, but has an atmosphere, and it's methane, I want to say, is a primary, like NH3. The compound methane is kind of what's primary on that moon. I think that is so cool.
Is there plans to land there?
Yes, we have landed there. The Titan, Titan, is the name of that moon that orbits Saturn, and they have actually taken a probe and landed on Titan. And it's called, the probe's name is Huygens. Okay? So sometimes there's like satellites that orbit gizmos and land. That one landed. That's so cool. I know, you're like, really? So it transmitted for a while, but then the aliens got to it, and no, I think it just ran out of juice. But so, okay, so this is Uranus, and I believe this, I'm thinking an artist rendition. I don't think that this is a photograph of Uranus. Okay, but what's this? Axis, very good. You're like, I don't know, it's a pen. Yeah, okay, yeah, this is Earth's axis of rotation, very good. Earth's axis of rotation tilted 23.5 degrees, okay. Uranus's axis of rotation, bless you, is tilted. Okay, so if this is 23.5, okay, what degree you think is this?
Somewhere close to 90.
About 90, yeah. It's crazy. Okay, so basically, I don't know if it has a pole star or not, but if that's the sun, it basically orbits, it spins on its axis, okay, but it orbits like this. Okay, so if we call this the North Pole, check this out, there's the sun, okay, this is the North Pole, okay, this is 1/4 orbit around the sun, and we're going to talk, it takes a long time for, the farther away the planet is from the sun, the longer it takes to orbit the sun once.
Which planet was it that goes this way instead of this way? Like we're rotating this way, and then there's one that rotates this way.
Yes, this is the one that, this is Uranus that rotates this way.
Okay,
Yep.
that's what I was trying to.
Yep.
But two.
And actually, we kind of passed up on Venus, but Venus actually kind of spins backwards.
Oh goodness.
So I know, we'll talk about
How can they
Venus.
tell the axis of rotation, like a magnetic signature or something?
Yeah, that's one good way. Yeah, he's asking about, but actually the magnetic signature of, I'm thinking Uranus, because I've seen pictures, usually the magnetic signature kind of comes out from the poles, like emanates from the poles, but Uranus is really strange. It kind of actually still kind of has this kind of emanating almost from the equatorial region. It's kind of weird. It kind of slipped a cog. But how do we know how it spins? Well, I guess because we've kind of come close to them. Okay, another way we know how it spins maybe is there are features like, you've heard of spots on Jupiter, great red spot on Jupiter. You may have heard of the great red spot on Jupiter. Well, we can actually kind of see some surface features on these other planets, these gas giants. Okay, so this is Uranus, crazy. The blue guy. And Uranus, all the gas giants have rings and moons. And sometimes I turn that into a test question. Do the gas giants have rings and moons? And you'll say yes. Okay. After Uranus, we have Neptune, the second blue guy. And again, this is an artist rendition.
I'm slightly confused.
Yes.
So they're gaseous planets. Does that mean you could just fly right through them?
Does that mean you could just fly right through them? Sort of. Sort of. Gravity would be an issue, you'd feel kind of the pull of gravity, but as gravity aside, you could actually, if this is Jupiter or if this is a gas giant, we'll talk more about this, you could, if you could fly through, you could make a cord like that. If you got too close to the middle though, actually there's a rocky core there.
Oh.
I was going to say, what's keeping it together? 'Cause
Gravity.
If it's really gaseous, how does it not eventually release it?
Gravity, like, we'll talk more about this, but it basically got enough mass to create the gravity to hold the gases there. Because you're right, because helium on the Earth, you're like, helium on the Earth, right? Okay, but if the Earth had the mass of these gas giants, helium would stick around.
Okay.
How big is the rocky core?
How big is the rocky core? I think I've read it's kind of like, it's like it swallowed a baby terrestrial planet. So it's about the size of Earth, kind of think of it like that.
So do you think it could have been a planet like Earth at one point, but like all of a sudden it just...
We're going to talk about the formation coming up, and it's kind of like, it basically, if that's the sun, these planets out here, we're gonna find out, they had access to a bunch more stuff that would kind of coalesce into a planet. These stuffs that's closer to the planet, like your rocky, your Mercury, Venus, Earth, and Mars, they didn't have access to as much stuff, okay, as these guys did out here. So kind of when they started forming, they kind of started forming by the rocky part, the metals that makes it rocky, and then they kind of added on the extra stuff out here. Okay, and these guys were kind of less. Yep. So Titan, Titan, orbits what planet? Has the atmosphere? Saturn. Yes, it orbits Saturn. Very good. And one of my things I don't like is there is a planet called Triton, Triton, and it orbits Neptune. Yep.
Well, it kind of makes sense because isn't Neptune like the Roman god of
Yeah,
the seas,
okay.
and then Triton is like, I think, King Triton.
She's saying mythologically it makes sense for Triton to be associated with Neptune. Very good. I like that. That's an association I don't have, but I believe you. Okay. So you guys told me after Neptune is Pluto. Okay. So Pluto is no longer a planet. And if you were, and you guys are almost probably young enough that you're kind of like, yeah, whatever. I don't know, maybe you're not. But for kids these days are like, yeah, I'm fine with that. I like to say that Pluto is cooler than a planet, okay? It's actually called a dwarf planet. Pluto out here is so special that they had to come up with something else to call it because it's not really a planet. So in '06, what happened basically was this. Well, not this. Let me see if I have it. In '06, well, I'll put up the whole thing. In '06, a grad student who needed a project basically took his fancy telescope and started looking out here. Now, if I'm out here, I'm kind of like Pluto and Pluto. She's like, dude, I am so going to find, at that time it would have been a 10th planet, okay? Well, out here, and maybe you might remember this, out here there's a bunch of crumbles, there's something called the Kuiper Belt. And then beyond the Kuiper Belt, there's actually something called the Oort cloud, which goes around the whole solar system. Okay, so what this grad student found was basically another beautifully spherical object, and he called it Eros, I think, the goddess of strife. So he called that object Eros, and he's like, 10th planet. Okay, it's bigger than Pluto, it's spherical, okay? So now actually we have these two criteria, orbit the sun, Pluto, Eris. Spherical, Pluto, Eris, okay? This third criteria, actually Pluto and Eris both fail. If you look out here and kind of take the track of what the planet, how it orbits the sun, and look to see if it has any extra stuff there, miscellaneous stuff, in its track, okay, that means it has not cleared its orbit. We're going to talk about the formation of planets. The formation of planets, basically, as they form, they clear their orbits. They gobble up everything and it becomes part of that. Okay? Yes?
So if Pluto were to clear its orbit at some point, would it be reconsidered a planet?
Probably.
Does that just mean that there's like a certain area around it that has things in it that then they don't consider it a planet, but if they add it to itself then and there's nothing around there, then it's a planet?
Right.
Is that kind of how?
Yeah, exactly. I think that's what she was kind of saying, and so it's like, well, what if it goes ahead and I think it's mathematically impossible for it to clear its orbit at this point. But if it did clear its orbit, and actually maybe we should make it a mission to kick everything out of the orbit, make it cleared, and then it meets that criteria. Green check mark.
Let's build a Dyson sphere first.
Dyson sphere?
Let's build one of those before we decide to go off messing with Pluto's orbit.
Okay, sounds like a plan. But here's one other thing. So I said dwarf planet, right? So Pluto's a dwarf planet, Eris is a dwarf planet, and I'm actually going to go into the solar system, okay? And I'm gonna go between Mars and Jupiter. What's between Mars and Jupiter? There's
Asteroid
letter
belt.
A, yep, asteroid belt, exactly. More crumblies, and actually there is Ceres, Ceres. Ceres actually is another dwarf planet. Ceres. It's in the asteroid belt. It's spherical, okay? Yep. It orbits the sun, and it has not cleared its debris either.
So if the asteroid belt goes away, then they'll have a planet in between.
That's right, if the asteroid belt gets cleaned up.
Is there anything, how far is the asteroid belt in Jupiter and Mars?
Let's see, Jupiter, Mars, asteroid belt. So what we're gonna see is if the sun is there, the terrestrial planets are pretty close together, okay? And then the asteroid belt, not too far from Mars, but I think it's a heck of a leap then to go ahead and go from the asteroid belt to Jupiter.
So, it's not too far from Mars, is it?
I don't think
Asteroid
it's too
belt?
far. You
And
guys
so
just
Mars
keep
could be,
thinking. Mars
Yeah.
could be where we locate and clear the asteroid belt of everything except Ceres. There you go.
well, I think it'd be good for mining, but.
Yeah, I was gonna say, Ty, when you said that, you guys have probably heard this, that they're looking at those asteroids as like for getting the precious metals from the asteroids. So that's kind of neat too. Put the almighty dollar and see where it goes. Yeah. So you can make some money while you're clearing orbits. Oh, this, by the way, oh my gosh. And my husband and I watched the New Horizons success, okay? Now, there's different types of missions. There's the missions where it lands on the object, like Titan had something land on it, right? There's the things where they insert an orbit, and they take a bunch of pictures, a bunch of great data, and sometimes they go ahead and crash, you know, that sort of thing, on purpose to get some other great data. And then there's the flybys. And New Horizon was a flyby. Can you imagine? I can't remember how many years. Oh my gosh, I think it was it more than 10? Was it 12 years? Basically, New Horizons left the Earth, okay, and if you listen to that podcast, the Star Talk will talk about something that's trying to get way far out there can actually kind of steal some potential energy from an object, kind of assist it to go farther. Anyway, New Horizons took these pictures. Can you see a heart there? This is Pluto. This is Pluto. It's got a heart.
Oh, yeah, because
Yeah.
the other side, it's like,
I got a T-shirt that says, "Now can I be a planet?" It's got the heart on it. It's like Pluto. I know. You're like, oh my gosh. So anyway, another cool thing about New Horizons was, let's see, Tannenbaugh. Let's see, discovered in 1903. Actually, Clyde Tannenbaugh. I might be butchering his last name, but Clyde was the dude who saw Pluto for the first time. And he could see it basically, it was a planet because it was moving against the background stars. What a rush, okay? So anyway, really kind of good work there, Clyde. So when he died, they took his ashes, and some of his ashes was in New Horizons. Isn't that not cool? I know. I love it. They probably felt so bad because they demoted it and everything, so anyway. I know. That is so cool. So that's all.
when did they decide that Pluto wasn't a planet anymore?
In '06. Yeah, and it was a joint decision. It actually was an international thing. So the scientists and, I don't know, laypersons too, but attended a convention where they discussed it. And honestly, I think it makes sense, because otherwise you would have added Eris, and then all those other things out there would have become new planets, and that would have been complicated.
So I remember when that happened. I was like in like 4th grade.
Mm-hmm. This is traumatic.
I was kind of like, okay, whatever. It's still like
Yeah.
a planet, just like a dwarf planet.
Yeah, it is. And it kind of, if you kind of look at the solar system as a whole, we got these rocky ones, we have the asteroid belt, then we have these gas giants. And Pluto, honestly, bless its heart, is more like it's more like an icy, rocky, it's not really a terrestrial planet, it's more like what we call comets, basically. We usually think of comets as, ooh, across the sky, but there's icy, chunky thing, that's a comet out here, okay? When it kind of comes close to the sun, it starts fizzing, okay? And that's when we see it. but it's out there.
Is it smaller than our moon, Pluto? Or
I think it might be comparable in size. I can't remember the size, but Pluto actually has 5. I think they discovered a 6th, but Charon, you kind of see Pluto and Charon, and Charon is a moon that orbits Pluto, and it's similar in size, so actually they have a common center of mass. Instead of Charon orbiting Pluto, it's so big that, so Charon's pretty big. So we love Pluto. Okay. Now, oh yeah, I wondered where this was. So this is a table in the back of your textbook. I really like it, okay? So we're going to take a look at the columns right quick. Of course, you see the planets in orbit, okay? And here's Eris that I was saying. What is an AU? Astronomical unit, yeah. And what is it?
Distance between Earth and the sun.
Yep, the average distance between the Earth and the sun, exactly. So that's kind of how far away they are, kind of relative sizes there also. This next column, okay, talks about how big it is, its radius, how massive it is, and its density. This is kind of a fun one. When we start talking about Jupiter, or Saturn, excuse me. Let's find the density of Saturn. Density of Saturn is 0.70 grams per milliliter. The density of water, which maybe you don't know or don't know, but the density of water is 1. So if something like Saturn is less dense than water, what's it going to do? Like this pen is more dense than water. So if I had a thing of water here, it would sink. Styrofoam is less dense than water, so styrofoam floats. Yeah. So Saturn actually would float in a big old tub of water. I think all the other planets would sink. Okay. Some things we've been talking about. This next set of columns is kind of similar to if you think of Earth. How long does it take for Earth to orbit the sun once? To orbit the sun?
1 year.
1 year. Yep, 1 year, 365 days, exactly. So this is actually saying how long does it take the planet to orbit the sun. Okay. So when it switches from like Earth to Mars, it's like Earth years. Okay. So in other words, I mean, this is just kind of fun things to think
29
about.
Earth years for Saturn to go around?
Yep.
Wow.
Yep. He's saying, so down here, it takes Saturn 29 Earth years to complete one orbit about the sun.
1 year.
Yep. So if you're about 60 years old, you know, Saturn's gone around twice. Yeah. So I'm not 60 yet, but.
So like Pluto, we're only really gonna see a fraction of what Pluto actually looks like. If like we look through a telescope or something. Because like in 248 years, it's gonna be in a completely different spot, or it's gonna be back to where it was, but it's gonna take 248 years to happen.
Mm-hmm.
So it's like we're not really getting the whole deal from Pluto or anybody else. It's
Well, yes and no, because that's how it's going to relocate relative to the sun.
but it's
But
still
how long
rotating.
does it take to, yeah. So it's spinning, so we see all sides of it, but yeah.
We're never gonna see it in the same spot
Right.
again, probably.
It's called configuration, like it's not going to be in the same configuration exactly. I love it. Yep.
It's like barely moving out there.
Yeah. Well, remember that's what Kepler said. Kepler said that the farther away a planet is from the sun, you
Slower
know,
does
it
it go.
moves more slowly. Yep.
Okay.
Is it like slowing down? Do you think eventually they'll just be like stopping?
Well, there's the conservation of momentum, so
Yeah.
it should,
Keep it going?
angular momentum, and yeah, it should keep going.
Unless something like crashes into it.
That's true, unless something crashes into it. Yeah. Or these kind of flybys, these assist gravitational poles, they take a little bit of energy, but I think it's fine. So one of the things, let's find Jupiter. How long does it take to complete one spin on its axis?
9.93.
Yes. So Jupiter, the largest planet, I just think that is amazing. Okay, so it spins on its axis, and right there, that last column says that it's tilted only 3 degrees. So it's pretty close to being, okay? So it spins once every about 10 hours or so. So one of the cool things in the telescope is the Great Red Spot of Jupiter. Okay, it's like in the clouds of Jupiter. It's been there for like, I want to say, pushing 200 years. It's a storm, I know.
Storm.
Yep. And so you can actually see that, if the seeing is good, from a telescope here on Earth. You can see the spot. And so people at the observatory will do their homework, and there's apps out there for Jupiter that will tell you where the spot is. It's like, oh, the spot will be coming around, and be prepared to see it in your telescope, or no, the spot's on the other side. So I think that's kind of cool. Of course, you see the, just a few more things here. So you see the Earth's tilted axis of rotation, 23.5 degrees. We talked about. What's the tilt of Uranus's? Yeah, check that out. So you guys told me this is 90, so 97. Okay, so it goes a little bit like this. Okay, yep. So basically, Uranus spins like this. Okay, wait, it doesn't spin like that. Actually, its axis of rotation is tilted 97 degrees. What about Venus? What's its axis of rotation tilted? Okay, let's see what that looks like.
Yeah.
Okay, so this is 0. This is 90. Okay, what if I were to go all the way from here to here? What angle is that?
180.
180. Yeah, half a circle. So 177, about like that, maybe.
I mean, it's upside down, kind of.
Yes, it's upside down. And
So-
that's actually, it's instead of going counterclockwise, okay, it's still going counterclockwise, but if you look up here, it's going clockwise.
Oh my god.
So it's like going from like the angle is like taking the North Pole.
Yes, the angle would be taking it as it's perpendicular to the plane of the ecliptic.
Okay.
So this is the plane of the ecliptic we talked about. This holds all the, it's like the record, okay? Okay, no records anymore, CDs, okay? And then 90 degrees is 0, if it's perpendicular, 0 degrees, and then you tilt it from there. Yep.
Yeah, I was just wondering like why like instead of 177.3 it could be like 2.7 degrees from the other
Oh,
axis.
yeah, I don't know. I'd have to think about that, but yeah.
I mean like it makes
The
sense like
axis-
the North Pole. But
Yeah.
The excess tilt seems kind of, I don't know, important.
Unimportant? Oh, bite your tongue. Why do we have seasons, young man?
I mean, because
We have seasons because our axis of rotation is tilted. Yes.
But I mean, whether it's like up or down, does that really matter?
It makes it interesting. Venus, right. Okay, what other columns do we have? We have the surface temperatures. Now, what does K stand for? What temperature scale is that? Kelvin, very good. Now, one of the things you guys probably didn't need to know, but I'll tell you, if you want to convert from Kelvin to Celsius, you subtract degrees Celsius, you take the Kelvin and you subtract 273 units. So I'm like, all right, so let's see, let's take 60 Kelvin. 60 Kelvin seems pretty warm. Okay, but if you subtract 273, you get negative 213?
it's kind of cold.
Yeah, negative 213 degrees Celsius. And I don't know what that is in Fahrenheit. I'd have to Google it. Okay? But that's the surface temperature of Uranus, negative 213 degrees Celsius. What's the lowest temperature anything can ever be on the Kelvin scale? 0 Kelvin. So 60 Kelvin's pretty cold. What's that?
The absolute 0.
Absolute 0, yeah. That was my point. Okay. And then we'll be talking a little bit about this. What are they made of? And we've already been talking about it. We have our 4 inner planets. Okay, then we have our 4 gas giants. Okay, so the first 4, what are they made of? Rocks and metals, rocks and metals. I also like this, again, it's in the back of your book, I think so, or maybe it's within the chapter. I might be wrong on that. It says, does it have moons or rings? And I kind of do this on your tests. Do the terrestrial planets have rings? No, terrestrial planets do not have rings. And like I said, you already know Earth has one moon, and we're gonna have to see a picture of Mars moons. And Mars has 2 moons, but they look like potatoes, I'm just saying. Okay? And then actually we skip here, check this out. This column here about moons, 67, 62, 27, 14, 5, 1.
Yeah.
Like, they all got moons.
So are they always smaller than the planet, or?
Are the moons smaller than a planet? Well, I think that the moons can be similar sometimes in size to a planet. Okay? But the reason they aren't a planet is because if you look back at the criteria that kicked Pluto out, they don't orbit the sun, they orbit another planet. Yep. So here you go. If you were to take one of the Galilean moons around Jupiter, kick it out, and have it orbit the sun, oh no. You planet builders, you. Yeah.
So if, like, going back to like something like crashing into Pluto or Eris, so let's say like something like just ginormous knocks into them, could they possibly be considered comets then? If they like go off their orbit and?
Oh, yeah. She's saying, what if you were to pick on Pluto, which is kind of like a rocky, chunky, rocky thing out there, and give it a nudge, and basically change it from orbiting the sun in a nice elliptical pattern to basically something parabolic, where you just basically say, okay, Pluto, you're going to go on into the inner solar system, just like other comets do. You're going to orbit the sun, and you're going to fizz. Okay, and yeah, it'd be a comet then. I don't know. I think so. It would be a fizzing dwarf planet.
Okay,
What's that?
so I finally got the calculations right. Pluto orbits the sun at around 10,619 miles an hour.
Oh, so check that. What we think is just kind of dogging it is really pretty fast.
Yes.
Is that your point?
Yeah.
Okay. Can you, yeah. Very good.
Well, first I took the average AU of 93 million miles from Earth to the Sun, and then I times it by 39.5 to get the radius, and then I took that times 2 times 3.14 to get the average circumference. Then I just divided down from 248 years until I got out.
So aren't you glad I take the math out of this class?
I like
that would make
math.
it more
Good job,
fun.
Shay. Good job.
Yeah, that's cool.
That is very cool.
I was determined.
Oh, okay. Very good. So as I was getting ready for kind of the end of this, or what we need to talk about now in this chapter is, it's almost, I won't say a love story, but it's like the formation of our solar system. And of course our solar system is the sun and the planets and the asteroid belt and the comets and the Kuiper belt and the Oort cloud. I mean, that is our solar system. Okay? So as we talk through it, we're going to apply the scientific method. And I'll tell you, though, what I'm going to do is kind of stick with what your book does. And there's ongoing research in this area of the formation of our solar system. Okay? So, of course, we have observations. I mean, like, duh, right? You can't just, like, make it up, although we want to. We can a little bit, but you can't do it on a test. Okay? In real life. So we have observations, and then from those observations we come up with our best guess. That's our hypothesis we kind of talked about in Unit 1. And then we gather more observations, and we continue to kind of support that hypothesis, or we might need to revisit the hypothesis and tweak it. Okay, but if it's actually kind of still continues to be, our best guess seems to like fit with the observations, and we can elevate it to a theory. Yeah, exactly. So things that we observe, motions. The planets go counterclockwise, we've been talking about, okay? And they are actually, their paths are ellipses, just like Kepler said. Most planets rotate. Now, rotate means spin, counterclockwise. Which planet spins clockwise? First letter V. Venus, yes. Okay, so most, okay. Moon-wise, or actually, if you look at like Earth and Earth's moon, capital M, there is a counterclockwise thing going, okay? The moon spins counterclockwise and orbits the Earth counterclockwise. Okay, so we kind of have that sort of thing going on. So those are observations. Another observation that needs to fit into the story of the birth of our solar system, another key observation was what we've been talking about. We got the rocky ones, we have the asteroid belt, and then we have the gas giants. And then after the gas giants, we kind of got these icy objects. Pluto is an icy object, icy rocky object. And then here, actually, this table kind of summarizes some things with the Jovian planets, the gas giants. Do most of them have moons?
Yes.
Yeah. Most of them have rings?
Yes.
Yeah, so we kind of have to, that has to, something makes sense there too. Okay, asteroids and comets. Yes, Pluto, the dwarf planet, if it started to fizz, I think I'd want to call it, instead of a fizzing dwarf planet, I would call it a comet. Okay? So we have, I call them crumblies, and actually the first chapter in Unit 3 talks about the asteroid belt. And kind of out here, we have, I called it the Kuiper belt with a K, and out here, it starts with letter O. What's this? Oort cloud, yep. Okay, so those kind of crumbly things. The difference between an asteroid and a comet is asteroids don't have an icy component, and comets, asteroids are rocks, and comets are rocks and ices. Okay, so comets are a little bit more.
So is that what they look like when they go across the sky in that picture right there?
This one, yes.
Would that be the same as a falling star? Or?
Nope. I'm glad you brought that up.
Because it looks similar. I've seen something like that the other night while I was sitting in my car and I watched it. It was like bright orange and green and it went across the sky.
I think you saw a falling star, a shooting star.
Oh.
Like
Did you
I'm.
say last night? The other night. It was like.
Did you see? Did you make a wishes? Yay! So when you see a shooting star, it's not really a star at all. We call it that because it's kind of a. But if you see a shooting star, if this is the Earth, okay, what's this? Above the Earth, the atmosphere. Yep. So actually, that's all in about how you see a shooting star. Basically, you see kind of a random chunk, and sometimes they aren't entirely random if it's a meteor shower, basically fall through the Earth's atmosphere and light up. Mm-hmm.
So why does it light up?
It's disintegrating, it's ionizing. It lights up, I think, probably because it's getting hot, too. Okay? And so kind of that streak, it depends on a few things, kind of the nature of the thing that's falling. Like different elements will give you different colors, kind of like we talked about before. And then kind of if it's at a glance, like you'll see a nice long streak, or if it's kind of straight on, you'll see like a little short, okay? Yeah. And it's not really a falling star because if you were to kind of take their trajectory back, there was no star that actually fell. It was just, you didn't see anything and all of a sudden you see the streak.
So where does that component go? Does it never hit the actual Earth itself?
Well, that's a good point too. So, and I don't know what this has to do with, I think it has to do with how big the chunk is probably, but a lot of times they basically mostly burn up as they're coming through the Earth's atmosphere. Now, with that said, there's these things, well, I'll put it this way. Now, if it kind of leaves a chunk, okay, so this is this is a meteorite.
Right.
This is a meteor as it falls, and a meteorite as you pick it up. Yeah, sorry.
That's what
Meteoroid, meteorite. Yes, it's a meteorite. It's the rock. It's the space rock. Yes.
Oh, how cool.
Mm-hmm. And there's like this, I haven't done it, but there's kind of this, if you read on the internet about micro, as in really small, micro meteorites, oh my gosh, you can actually find little tiny space rocks that aren't anything big, but basically they came from space. And the Earth picks up, I don't know, tons of mass each day from micrometeorite stuff hitting it.
They need to make a little, like, you know how they make a metal detector?
And that's actually,
They need to make one that's like a meteorite detector.
if you read about it, it will tell you one of the things that you can do is to try to look for those, use a magnet, because a lot of times space rocks have a lot of metal in them.
Cool.
Yeah.
Sorry.
So, I know. So anyway. So a comet, this is a comet, okay?
Yeah.
And comets will, although we did have a fast-moving comet, but usually comets If that's the sun, and this is the chunk that's leaving probably the Kuiper belt or the Oort cloud, and it's gonna come close to the sun, it's gonna start fizzing. But I mean, it takes, I don't know how long, maybe a month to do that, okay? And will it go fast or slow when it gets too close to the sun?
Fast.
Fast, exactly, just like we talked about. So kind of zoom around and they'll start to go slow again. So basically, you'll see these over the course of maybe about a month move against the background stars. So if you guys are the Earth right there, okay, you're going to see it kind of approaching the sun, and I don't know what point it starts fizzing, but when it gets close enough, gets heated up, it starts to get the tail. And you'll see it kind of move against the background stars. So if somebody says there's a comet out tonight, you're like, okay, well, it's probably going to be out maybe tomorrow night. It was out the night before, too. It's kind of against the background stars. That's totally different than that streak that you guys enjoyed.
Okay.
Yeah. So,
What is the Oort cloud?
what is the Oort cloud? I kind of go out here. The Oort cloud, it's basically this humongous spherical stuff that didn't become the sun or a planet within our solar system.
So it's just like ice and rock? And
Yep. It's what I call leftovers. I think your textbook does too.
And it encompasses like the whole solar system?
Yes. The Oort cloud goes around the whole solar system. Yep.
I can do the math of that too, if you want.
No, I don't have the energy.
How can we even see out if that's like...
Well, maybe that brings up a good point. Now this might involve some math. So, like if this is this is Mars and this is Jupiter. If you look at, and what's between Mars and Jupiter?
The belt.
The belt, yep, exactly, the belt. Very good.
Sorry.
So a lot of times on science fiction movies, you'll actually see where these belt asteroids or asteroid belts, the asteroids in the asteroid belt, they're close together. They're really far apart. They're like, hundreds of kilometers between little chunks. So I think maybe to your point, when you start looking at I think they're like 100 AUs, like if this is the sun, out to like 100 AUs, that is the Oort cloud. That's a long ways away. Okay, so you kind of got the distance thing going, the big sphere. Okay, very good. Well, we didn't get to just do your best on let's pick up here on Friday. Just do your best on this chapter assignment that's due on Friday. But it's due at the end of the day, so if you want to come to lecture and hear about it and then write it up, I'm sure we'll get through this chapter on Friday. Good questions.